Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at the solutions to the null equation for a second-order linear differential equation with constant coefficients. That's quite a bit, but here's the problem that we were looking at. We were solve the problem of ay double prime plus by prime plus cy equals 0. And what we said is, we said that if we let our null solution be some e raised to the st, we could substitute our null solution in, and we did this. We let the null solution be e to the st, so this gave us that y null prime is s e to the st, and y null double prime was s squared e to the st. So then what we did is we substituted. So we substituted our null solution and its derivatives into the original equation. That gave us a s squared e to the st plus b times s e to the st plus c times e to the st is equal to 0. We factored out an e to the st, and this gave us a s squared plus b times s plus c times e to the st equals 0. And then we said that because, let's come over here, we said that because e to the st is not 0, we solve, let's do that. We'll solve, it's the characteristic polynomial, the characteristic polynomial, of, and that's this. This piece right here is our characteristic polynomial, and that is what we're going to do is we need to find the solutions to as squared plus b times s plus c equals 0. And we said that our solutions then are of the form s equals minus b. We're just using the quadratic formula to solve this quadratic equation. So I have minus b plus or minus the square root of, I have a b squared minus 4 times a times c. All of that is divided by 2 times a. Okay, we're going to pause the camera here and we're going to move over to some new board space. Now we're going to pick up, this is our solution, and what we want to do is we want to find a more meaningful notation to represent our solution here. And so what we're going to do is we're going to do something that you've probably not spent much time doing. That is, we've always tried to simplify our answers. In this case, we're going to unsimplify our fraction based on our common denominator of 2a. So let's do that. Let's unsimplify our solution. So I'm going to write this as s is equal to a minus b over 2a plus or minus. Then we have the square root of b squared minus 4ac. All of that is over 2 times a. 2 times a. Now, but let's continue. What I want to do, though, is I want to continue by design. And the first piece is already on the board. And that is, the common notation is we say this. We say let, and we're going to use, that's a lowercase p, let lowercase p equal b over 2 times a. So if we do that, then we can continue. So that gives me that s is equal to, we're going to do a few things here. First off, we get a minus p plus or minus. Now we're going to continue to unsimplify. Notice that I have another fraction. So what I'm going to do is put this 2a into that radical and then deal with my fraction. So I'm going to make this a b squared. Oops, that is just on the wrong spot. So let's write this as b squared minus 4ac, and we'll put all of that, well, if we want to put the 2a back inside of the square root, we need to square both of those. So now I have a 4a squared. I'm going to put all of that, we have this big square root now. And then let's carry that over to our next step. Our next step is going to be now that s is equal to, we pick up, we have s is equal to, let's apply the same idea. We have minus p plus or minus. Then we have under our square root, we're going to put that here, we have b squared over 4a squared minus, and we have 4ac over 4a squared. All of that is now under our radical. Okay, but notice this. So notice, what do we have? Notice that if p is b divided by 2a, then p squared, well, that's going to give me b squared over 4a squared. But look at that. That is this term. So now I can write my first term in the radical as p squared. Okay, so we've got that. The next thing we want to do is I want to look inside of my square root. And in order to do that, let's get another color of chalk. I have these pretty yellow and pretty pink colors. Notice this. I can cancel 4's. I have an a and an a squared. I can trim that down. And notice that what I'm left with here is c over a. And we've seen this before. Notice that if I was to take my original differential equation of ay double prime plus by prime plus cy equals 0, there's two things going on here. One, I could divide everything by a, and so this is the same as saying y double prime plus b over a y prime plus c over a y equals 0. But we saw earlier that this coefficient of c over a was the same one as when we had my double prime, the mass attached to the spring, plus by prime, plus the damping coefficient, plus the spring constant ky equals 0. And now if we apply the same idea of dividing by our leading coefficient, I have y double prime plus lowercase b over m times y prime plus I have k over m times y equals 0. And what we said that omega was equal to the square root of k over m, or that omega squared is k over m, or if we look at our original problem using a, b, and c, omega squared is c over a. I want to do one more thing, and that is we're going to call this omega n squared. It's the natural oscillating frequency of the spring. And like when b was 0, we saw this as undamped harmonic motion. So look at that. That right there, that's this. So if I have one more step, I can say that S is equal to negative p plus or minus the square root of p squared minus the natural frequency squared. And that's where we get our new notation. In our next video, or in our next videos, we're going to take a look at the discriminant here. As this number here changes, what does that tell us about the solutions that we're finding? Thanks for watching, and see you in the next video.